space of matrix A is equal to the column space of A transpose. If A is an invertible 5 by 5 matrix, what is the rank of A? 5, right? So there's actually like a few steps in the argument to get there. So remember, you have to know what the rank of a matrix is in order to answer this question, which is the dimension of the column space. And the dimension of the column space is the number of pivot columns in the matrix. So there's like a few steps to get here. So we said because A is invertible, that means it's row equivalent to the identity. Remember that theorem from the invertible matrix theorem, which means it has 5 pivot columns, which means the dimension of the column space is 5, which means that the rank of the matrix is 5. True or false? If A is row equivalent to B, then the row space of A equals the row space of B. That is true. That is not true of column spaces, right? But it is true of row spaces because the way you make row equivalency is by taking linear combinations of the rows and replacing them. Okay, so today we're going to talk about row space, the rank of a matrix, and develop the rank theorem. This is a little summary diagram to help with some of the terminology from this section. So if we think of this A times X as a transformation, a linear transformation, where your inputs are X's, the things that you multiply A by, and your outputs are A times X's, so that's your range, A times X. The null space, we already know the definition of the null space of a matrix is the set of all things that go to 0. And then your column space of a matrix is just the set of all possible outputs of A times X, all linear combinations of the columns of A. And now we're throwing in row space of A, which is defined as the column space of A transpose. So we already know what column space is. So if you just take A and transpose it, that would be the column space of A transpose. It's the row space of A. And then the null space of A transpose lives over here. And the column space of A is the row space of A transpose. So we're going to do a lot of, like, you can memorize all the equivalencies, but as you work with it, it'll start to be like, oh, of course, those things are equivalent. So we'll do some examples. Should make it clearer. All right, so I have 3 row equivalent matrices, A, B, and C. So A is the original matrix, B is echelon form, but not reduced row echelon form, and then C is the RREF. All right, so I'm just not going to try to like do anything fancy yet. We're just going to try to wrap our brains around what do we mean by col A, row A, and null A. So the definition of the column space of A is linear combinations of the columns of A. So something in col A is any linear combination of the columns of A. So we could do 2 column 1 minus column 4, right? That's a linear combination of some of the columns of A, and that would be, I'm going to have to write it out. I can't keep all those numbers in my head. 2, 6, -6. That's 2 column 1. Column 4 is -1, 0, -2, 2. So I get 3, 0, 8, -8. That is one element from col A. Just any linear combination of the columns of A. The row space of A, that's defined as the set of all linear combinations of the rows in A. I'm going to run out of space. Might get a new page here. Okay, so we already did col A. So row A, a linear combination of the rows of A. So you think of the rows in the matrix as vectors. You can either write them vertically. Each one has 7 entries. The rows of A all have 7 entries. So you can either write them vertically because that's how we're used to picturing vectors, or you can write them horizontally with commas because that will just remind you that like these are rows. So it's whichever one sort of makes more sense to you. So let's say I will just do 3 row 1 plus row 3, right? Just I'm making up any random linear combination of the rows of A. So that would be 3 times row 1 is 1, 2, 0, -1, -4, -2, 0, plus row 3, which is 3, 6, 0, -2, -8, -4, 0. Again, you can write these vertically if you're more comfortable with looking at vectors vertically. Your book often does rows horizontally, just because they're already written horizontally because they're rows. So this just kind of reminds you I'm working with a row space. So this is 3, 6, 0, -3, -12, -6, 0, plus. So this is just a single element from the row space. 6, 12, 0, -5, -20, -10, 0. That is one vector in the row space of A, linear combination of the rows of A. You also could have taken a linear combination of the rows of B or C, because they're row equivalent, and the way you find row equivalent matrices is to take linear combinations of the rows. All the rows of B are linear combinations of the rows of A, and same for C. So for row spaces, you can use any of the 3 matrices. Column space, that's not true. You have to look at the original matrix A. All right, and then for null A, I'm going to get another fresh page here. Make myself a note to give more space for future semesters. Sorry about that. All right, so anybody remember how to find the like what's in the null space? Yeah, so we're looking for something times A, like we're looking for A times what that gives 0. So you would just set up an augmented matrix and solve this. I already row reduced, right? So I would just I would say C augmented with 0 is how I would solve this. And the solution set says x1 plus 2x2 equals 0. There's some zeros augmented on here if we're trying to find the null space. And then the next row says x4 plus x7 is 0. Oh, sorry, x3. And then we've got x4 plus 4x5 plus 2x6 is 0. My last row is zeros, so that doesn't give me any information. And then my free variables are my non-pivot columns, so x2, x5, and x6, and x7. 2, 5, 6, and 7. So any x1 through x7 that satisfies those 4 equations, 3 equations, is going to be a solution, which means it's in the null space. So let's see if we can come up with, might be easier if I write it, each of the basics in terms of the frees. So then you can pick anything you want for x2, x5, x6, and x7, and you calculate the x1, x3, x4. So what do you want to pick for the 4 free variables? Zeros or ones? Yeah. Let's pick zeros. So x2, 3, 4, 5, 6, and 7. And then you calculate the x1, x3, and x4, which would all turn out to be 0. 3, 4, 5, 6, 7. There we go. Yes, why would I have, how do you know that? Yes, 0 is always in the null space. For every single matrix, 0 is in the null space. So I didn't have to do any of this work. I could have written down the 0 vector. As long as I know how many elements are in it, 7, right? We would have had it. But just so that we don't waste the work, let's pick another one. One more vector that's in the null space. I'll pick ones, right? For x2, x5, 6, and 7. I'll pick ones. So then x1 is negative 2 times 1, negative 2. x3 is negative x7, so negative 1. And x4 would be negative 4 minus 2 is negative 6. So I picked 2 elements. Those are both in null A. Okay, so let's answer some questions about dimensions here. What is the dimension of the column space of matrix A? 3, right? Because so the way you find the dimension of the column space, it's the number of pivot columns. So we go to the final row reduced matrix and we say there's 1, 2, 3 pivot columns. So that's the dimension of the column space. Just a little reminder, that is the dimension because the way you find the basis for the column space is to identify the pivot columns and grab those columns from the original matrix A. There's 3 of them, so that's going to be the dimension of the column space. How about the dimension of the null space of A? 4, because that's always going to be the number of free variables. Because as a reminder, the way you find a basis for the null space is you solve for the null space like we did here. And then the number of free variables is the number of vectors you have when you write the solution, and those 4 vectors would be your basis. So there's going to be 4 of them, so that's the dimension of the null space, the number of free variables. What's the rank of the matrix A? The definition of rank is just the dimension of the column space. So we already answered this question. It's just another way of asking you what's the dimension of the column space. And the dimension of the row space of A? 4. Yep. Yep. Because that is the dimension of the column space of A transpose, right? Or I could just tell you or remind you from your reading that the way you find a basis for the row space is you look at the non-zero rows of the row reduced matrix. And you can either take those 3 rows from the reduced matrix, or you can take those 3 rows from the original matrix. Doesn't matter. But there's 3 non-zero rows in the reduced matrix. So the dimension of the row, oh wait. Yeah, so I guess it's 3. Thought it was 4. Nope, it's 3. It's 3. All right, so where do these guys live? So call A, the vectors in call A. Let's look at our example vector. What are what? This example vector, it lives in R4. So call A is a subspace of R4. Okay. Null A, let's look at our calculations for null A. This was my example of an element of null A. How many entries are in that vector? 7. So the elements of null A live in R7. So it's a subspace of R7. And row A, if you take linear combinations of the rows of A, R7. Yeah, because there's 7 entries in each row. Yeah. Okay, the column space of A transpose. So if I took A, this matrix A, and you make each row a column, and then take linear combinations of the columns, the entries are all going to have 7. The vectors are all going to have 7 entries. So this one's going to be R7. The null space of A transpose, R4. Yeah. So if you have a 7 by A transpose is 1, 2, 3, 4, 5, 6, 7 by 1, 2, 3, 4. So this is A transpose. So remember the null space of a matrix is what do you multiply by to get 0? And this is 7 by 4, so what you multiply would have to be 4 by 1. So the null space of A transpose is R4. Don't hesitate to make yourself little pictures like this. Like I still always have to draw these little pictures in order to figure out what space I'm supposed to be getting answers from. The row space of A transpose. So this guy is A transpose, this 7 by 4. So if you take linear combinations of the rows, each row has 4 entries. So it's going to be a subspace of R4. Okay, so if we're trying to find a basis for col A, row A, and null A, I'm just going to ignore this. I just wanted the matrices back. Okay, basis for col A, row A, and null A. So a basis for col A, to remind you, is the pivot columns of A. So you have to identify the pivot columns by looking at the row reduced matrix. It's column 1, column 3, and column 4. Take those from the original A, and that forms your basis for col A. So 1, 0, 3, negative 3. That's column 1, and then we need column 3 and column 4. 0, 1, 0, 3, and negative 1, 0, negative 2, 2. Your basis for row A are any non-zero rows of the reduced matrix A. And you can take them from the reduced matrix or A itself, doesn't matter. So I'm going to pick, I'm just going to take them right from C, so there's less like going back and forth. And I think I will write it vertically. So 1, 2, then 5 zeros. 0, 0, 1, 0, 0, 0, 1. It does not. Nope. And 0, 0, 0, 1, 4, 2, 0. All right, and then last we need a basis for null A. So I wrote down solutions to the null set a few minutes ago. I'm going to write it in parametric vector form. So my solutions for all of null A is negative 2, 1, and 5 zeros. X2 plus 0, 0, 0, -4, 1, 0, 0, x5 plus 0, 0, 0. So that's all of null A. It's not the basis, that's all of null A. And I got that by just writing the solutions that I wrote for null A on the previous page here when I was trying to find null A. I wrote the solution set like this, right? And what I just wrote on the other page was I translated that to parametric vector form. So that's just parametric vector form for the solutions for finding null A. And then the basis for null A is these 4 vectors from the parametric vector form. Oh man, I don't want to write them all again. Yeah, I'll just 4 vectors above. Yeah. Yeah, you could write that. That's fine. All right, how many vectors are in the column space of A? Not its basis, but the whole column space. Infinite. Yeah, because it's a set of all linear combinations of the columns of A. The number of scalars you can choose to put on as weights is infinite, so you get infinite combinations. So I want to come up with an example of a vector in col A that's not one that we gave on the first page and not directly an element from the basis. So I'm trying to remind you with this question that you can build every element in a vector space by taking linear combinations of its basis vectors. So any linear combination of vectors in the basis for col A. So I might do 2 times 1, 0, 3, -3, plus 3 times -1, 0, -2, 2, right? I just randomly picked some vectors from the basis of col A, put some weights on them, and add them together. So I'll get 2 minus 3 is -1, 0, 6 minus 6 is 0, -6 plus 6 is 0. Yeah, I didn't mean to do that. I could do a similar thing to find any vector in row A. It's not. I don't want you to grab it right from the basis or use the vector that we gave in part A, but take a linear combination of the vectors in row A, in the basis of row A. So here's my row A basis. I could add 2 of them together, and I get a linear combination. So maybe I'll add vector 2 and vector 3. Let's see. It's going to be 0, 0, 1, 1, 4, 0, 0, 1, 1, 4, 2, 1. Great. Thanks. And then an example of a vector in null A that's not the basis, not in the basis, and not the vector I gave in part A. So if in part A I was clever and wrote the 0 vector because the 0 vector is always in the null space, here I would be forcing you to come up with something different. And you would go to your basis for null A, throw some weights on x2, x5, x6, and x7, which we could do 1s, but we already did that one. Let's do 1s on x2 and x5 and 0s on x6 and x7. So we'll just add these 2 together. So we get -2, 1, 0, -4, 1, 0, 0. That's vector 1 plus vector 2.